In this video, we are going to continue talking about kinetics of a chemical reaction, and we are going to define the different types of chemical reactions that you need to be familiar with for this course. When it comes to kinetics, as we learned previously, kinetics had to do with the speed or the pace of a chemical reaction. And usually we look at this in terms of the reaction rate. By definition, the reaction rate is the measure of the change in concentration of the reactants or the change in concentration of the products per unit time. Kinetics of our reactions can be affected by a number of factors. They include the concentration of reactants. So if you increase the reactant concentration, because the system will have more collisions, then that increases the rate of the reaction. Temperature also affects the reaction rate of a chemical reaction. If you increase the temperature of a reaction, not only you have more collisions, but those collisions are going to be producing activation energy that is going to allow those reactants to get to products. And this is going to also affect the reaction rate by increasing it. Lastly, we have the addition of a catalyst. And a catalyst is going to be specifically a molecule that when it's added to a particular reaction is going to increase the reaction rate, but specifically is going to do so by lowering the activation energy of the reaction. If we look at the left side of the slide, we can actually see an example of a reaction and what happens overall without catalysis or without a catalyst and with a catalyst. So when we look at the following energy diagram, we can observe that the curve that is in the back that has that teal color represents a reaction with no catalyst. Rxn is my shorthand for reactions. If you take the same reactants, but along with them, you put a catalyst, we can actually observe that that is not changing overall the potential energy of the reactants or the potential energy of the products. In this example, we can see that this is an exothermic process because the potential energy of the products is lower than the reactants' potential energy. The addition of this catalyst, what is doing overall is that we see a reduced height in that peak for the activation energy, but it actually allows this reaction to get to product faster just because of the lowering of that activation energy. So in essence, the addition of a catalyst, what it does to the reaction is that that minimum that it is required to go from reactants to products is now lowered. When it comes to catalysts, let's understand that overall, they are not used up during the reactions. So what this means is that the catalyst just opens a gateway in order for the reactants to make products, but it is not going to be destroyed in the process. And most catalysts are going to be regenerated at the end of the reaction in order to be continuing the reaction in its progress. And overall, they are always regenerated. Let's now proceed to look at different types of reactions. Even though in previous videos, we have already seen a few types of reactions. Let's actually give them a definition. So for the purposes of this course, you guys need to be familiar with 5 different types of reactions. They include combination or synthesis. What a combination or synthesis reaction is that you will have 2 or more reactants that when they combine, they're going to yield a single product. We can also have decomposition reactions. In a decomposition reaction, we're going to have 1 reactant that splits into 2 or more products. We can have single replacement reactions. And in a single replacement reaction, we are going to have 1 element replacing another element. So if we look at these boxes of letters, we have element A, just as an example, and this is going to replace element B in the compound next door. So when we look at the product, then substance A now form a compound with the element on C, and B got replaced. In a double replacement reaction, this is just an exchange of partners that are going to happen between the 2 different substances in the reactants. In double replacement reactions, we are going to be assuming that if we have an ionic solid represented by A and B, A is going to be a cation, B is going to be an anion. C is going to represent a cation, D is going to represent an anion. And in this exchange of partners, we are going to generate new ionic compounds in which the cation of the first combines with the anion of the second compound to make a brand new compound called AD. With, again, A is the cation, D is the anion. Next, the cation of the second compound can combine with the anion of the first and is going to make a new ionic compound that is called C and B. Lastly, the last type of reaction that we have are combustion reactions, which we observed earlier that it is the reaction that happens in calorimeters whenever we're looking at food samples and understanding what is the energy stored inside the fat, the carbohydrates, and the proteins. So when it comes to this, let's understand that in a combustion reaction, if and only if your compound has carbons and hydrogens, when you combine it with oxygen gas, you are going to make CO2, water, and energy. And we already observed this specific type of reaction. Let's actually do an example in which we look at reactions given and then we classify them based on the classification that we just learned. For this, we are going to do the problems that we have in the following slide. So when we look at number 1, we can observe that here we have the compound HNO3, and then we have the single element nickel. When we closely look at the product, we see that now nickel is with NO3 and hydrogen is by itself. So this illustrates how this reaction is a single replacement reaction. When we look at the next one, we can observe that we have BaHCO3 and overall that produces BaCO3, water, and CO2. So in here, since we go from one substance into making multiple substances, this specifically is a decomposition. In the next reaction, we have this nitrogen gas combining with this oxygen gas, making a single product. So this is called the combination reaction, or in other words, a synthesis reaction. When we look at the next one, we see that we have KOH. So if we split this into ions, this is K plus OH minus. If we look at H2CO3, this is H plus and CO3 minus 2. When we do this, we can observe that in the product, we have H and OH combined to make the water. And lastly, we have K plus and CO3 2 minus to make K2CO3. So that means that this is a double replacement reaction. Make sure that you practice with the classifications of number 5, 6, 7, and 8.